Prelim is done.
Okay, and then I go like this, and I do this.
Yes, sure. That's why I'm graduate.
Are you like this is like some very modern art that super modern, yeah.
How do you check the data? So I did it.
Alrighty, folks. Good evening. So the plan for the rest of the evening is a little bit of a few things. The first is if anybody has something about Julia that they're really keen on learning about. It could be the compilation pipeline. It could be, how to do SIMD. I don't have the answer to that very well, but I can definitely read the docs probably faster than you can. If anybody wants to know a little bit more about sort of pre-compilation or the upcoming Julia C compiler, which compiles sort of static binaries, we can talk a bit about that. So yeah, if you have any burning questions, if you didn't understand something really deeply, if you'd like more examples of something, the rest of the time, I think we will probably spend sort of building a little package together of sort of miscellaneous things that seem like what quantum folks do, according to Stefan and Katie. Mostly Stefan, because Katie's examples were quite a bit over my head. And sort of implementing them a little bit poorly at first, maybe deliberately, and using a few of the tools that we have available to try and fix them. So if everybody's cool with the latter, we can go ahead and do that. But if you do have anything that you want to hear about, do let me know. We can always chat afterwards, of course. But last year, there were a lot of people who wanted to know very specific things about arcane lore and that kind of stuff. So yeah, just raise your hand if there's something, but otherwise, we will briefly look at the AbstractArray interface just so we have something to sort of contextualize what we're about to do. And then we will go ahead and start on a little package together. All right. So Julia was essentially built for linear algebra. That was the original intent. It was it inherits a lot from MATLAB, the matrix laboratory. Unlike MATLAB, where everything is a matrix of float 64, Julia is not like that, thank goodness. Unfortunately, that means that Julia has quite the array of arrays, and they don't always cooperate with each other. Some of that may be inherent to multiple dispatch and the design space, right? We can claim all we want that we don't have to cooperate with each other and we can write our own packages and they just happen to work together. But eventually the rubber hits the road and there are some difficulties. These show up in a few different ways. The first one is ambiguities. An ambiguity is something like, ignore that. An ambiguity is something like this. Our beloved foo is back. Bigger. Yes. Okay. I was like, why is he stretching so much? That's crazy. An ambiguity might be a function like this. X is sort of untyped. This stands for, the any typing. And then Y is a string. And then equals my favorite howdy. Somebody else comes along and they write X string Y any. And they wanted to say duty. I don't know. And if I do this and I type, we get a method error. This is ambiguous. Hopefully everybody sees why, right? We try to match everything all at once, everywhere. We have a string on both sides. foo number 1 takes a string in the second argument and anything in the first argument, and string number 2, or foo number 2 takes a string in the first and any in the second. So you have to resolve this. And Julia is very nice. It tells you how you need to do that. It says foo of string is ambiguous. And you can fix this. It's not too bad to do, right? I can write foo and our problem is solved, right? The problem is we have a lot of array packages in Julia, right? And the way that the matrix multiplication packages are written, the way that the matrix multiplication interface is written, is that somebody owns the matrix multiplication, right? Either the left-hand operand or the right-hand operand. And so if on the left-hand side, I have a block sparse matrix, and on the right-hand side of the matrix multiplication, I have, an unstructured sparse matrix. And I'm the author of the unstructured sparse package, and you're the author of the block sparse package. And then there's 50 other packages that also implement arrays. You can see how this would explode the number of ambiguities, right? Just for matrix multiplication alone. This is made far worse by parameterization. So if my string was a matrix with element types up there, that can sometimes get even worse. So I just wanted to mention the problem of ambiguities up front. I don't think we're going to encounter them as we look at things today. I think we're just going to be looking at how to write fast functions of your own. But that's kind of one of the last things I want to talk about, dispatch. This is one thing that if you work in Julia for more than 5 years or so, you will encounter problems like this when you're designing your interfaces. With great flexibility comes great problems or something like that. All right. So how do we implement an array in Julia? The basic interface for an array, one that you just need to read from, you don't need to write into, is just two functions, two methods. So I can do a struct my array of type T, element type T, sorry. I'm just going to stick a vector in there because I'm lazy for now and I just want to illustrate what's going on. Once I have that, I can construct, rand of 10. And there's my array. Float 64, just a 10 length vector. So what do I have to do in order to use my array? Oops, I made a big error. What am I missing? Anybody know?
Subtype abstract array.
Yep. So I have to start over. This is now your array because, like I said, we cannot rename things. And we need to be a subtype of abstract array. In fact, we're going to be a subtype of abstract vector just so we can get through this to the meat and bones. So your array. What in the? Oh, this is because we haven't done the work yet. So what happened here? I constructed an array, and what happens if we don't put the semicolon? Can you it tries to print it, and what does it try to do when it prints it?
The size of the array.
Yep. Tries to print each value in the array and needs the size to do that, and we haven't yet implemented the size. So it gives us this scary exception stack, but we can forge on ahead so long as I look back up and actually remember what we're typing. Whatever. All right. So to extend other people's functions, you have to be in their namespace, right? If I just write size of your array, I'm going to create a new function, right? This is just going to be the size function in my REPL. If it was in my own package, it would be my package's size function. I have to either import it specifically, when we build a little package here in a few minutes, I'll show you how to do that. Or I have to explicitly namespace it specifically with base. So I'll do base.size. And then how do I get the size of my array? Well, I'm just going to punt to the element type, or the child here. And now we have size of, what did I call it? X. I didn't call it anything. The next thing that we have to implement before, I don't want to get another error printing, is base.getindex. This is the bracket for grabbing a value out of the array. Base.index is, or indexing is desugared into base.index. So we just need to do something like this. Get index of X, your array. We can just do yeah.
Sorry, could you move the screen? I guess when you're typing towards the bottom of the screen,
Yeah,
I can't see it.
I unfortunately, I just had to remember. So thank you for reminding me. I can't like keep it up at the top.
Oh,
As far as I'm aware, unless somebody knows something more about iTerm than I do.
You might be able to quarter screen it and like.
Sure, that's not a bad idea. That works. So, see, but then it moves. I don't understand how to make it stop doing that. And then this thing gets in the way. I don't even know what that is. Okay. I'll just do indexing the same way here. I think this is a V if I remember correctly. And I'm just going to index basically like normal. So my your array up here should now be available, and you'll notice it prints just fine now. We have fully implemented the sort of read-only interface for abstract arrays. It's just two functions. Of course, that's just for a vector. For a matrix, it's a little bit more complicated. You have to return a tuple for your dimensions rather than just a single value. But if your underlying matrix is also a matrix, if this is just a wrapper, like we did here, then that's fine. Base.getIndex will take, two indices instead of just one. But otherwise, that's pretty much everything we need. We could, for instance, use this to do all sorts of different arrays. And we might look at a few before we move on, like a one-hot vector, or a matrix of all ones, or a matrix where the value is computed by some function of the indices, I plus j, or something like that. So the last function we are missing, if we want to do everything with this vector in the array interface, is base.setindex. Base.setindex is mutating, so we put the exclamation point at the end, and we have. I'm just going to look up the help here so we can see what it looks like elsewhere, and also so I can remember what the order of the arguments is. So here's the doc string. We can pretty much just copy that. And base.setindex, your array, X is the value. It doesn't really matter what it is. And then the indices, we just have one. And this is v of I equals X. And so now if we have our, I once again didn't give it a name, of course. V of 1 equals 10. So notice that indexing, I don't know if I mentioned it earlier, indexing returns the thing that you indexed. This is nice if you get a value from a function, you want to put it in a vector, but you also want to do something with it afterwards. That's why it behaves like that. So we have just implemented our first little vector. This will inherit the multiplication behavior and everything else from the AbstractArray interface. So kind of luckily for us, it won't actually inherit any of those ambiguity problems that I mentioned. Those only arise when somebody is trying to control, for instance, the matrix multiplication method. But because everything I've written just now only really pertains to my struct, I don't have to worry about most of these problems because somebody else owns the functions. So we can try to make a few lazy matrices here that act like bigger matrices, but save us a lot of space, right? So we can do an identity matrix, which is built into Julia, but we might want to do something a little bit different with it, like an int e value. Oops, VT. It's a bit of a misnomer as an identity matrix at this point, but let's see, we can do base.size of our identity matrix, a identity equals a.n, and then base.getindex a identity ij equals I equals j a dot b or 0 of element type of a. And we're pretty much done. So an identity matrix, fake identity matrix, as I mentioned, which is size 100 with value 5 inside. What did we forget this time?
I think it's supposed to be that big.
This one's new to me. What is even going on here? Base.size equals. Oh. There we go. For whatever reason, if you return for a matrix a scalar size, whatever this is happens. I believe this is the 1 by 1 by 1 by 1 by 1 by 1 tensor, all the way up until, I don't know, it gives up. I think arrays have a maximum dimensionality somewhere. So you can see we've got our identity matrix, our fake identity matrix with 5s all along the diagonal. And we can multiply with this, right? I equals that, and then I times rand 100, 100. And I assume that did something because I used rand and I actually can't tell. But the nice thing about this is that unless you're printing, it will only allocate 2 values, right? The value on the diagonal that you've replicated and the size. This is one way that, especially early on, Julia saved a lot of speed and memory against a lot of competitors that were still representing matrices, in relatively weaker formats, despite the fact that we knew for a very long time about these different formats that we could use. It's just very hard to fit all of them into a language that does single dispatch. Not impossible, but very hard. There are tools like Eigen, for instance, that do a good job of taking advantage of matrix structure, if I remember correctly. Let's see. We can do one more here. We'll just do the index matrix. So this is the one that is a function of the index matrix 1. How about that? This is a function of the index that you're at. For this first one, I am not going to give, this is going to be function. That sounds about right, right? And then this is integer, and this is n. And then we should be done. Excuse me. So we need to know the type for t. If you just give us an arbitrary function, could have an arbitrary return type. I'm going to do t equals type of. And you often see this where you sort of do this little bit of dynamic dispatch here. We're just going to take the value of the function at 1, 1. And Julia is pretty good at constant propping these away. So if your function is constant, if Julia can figure out that it knows how to calculate your function at 1, 1, which for most integer functions it does, then this will be done all at compile time. Matrix 1 of t f m. I'm missing a parentheses, or I have too many.
And you on the second line.
On the second line? Yep, thank you. And we can do base dot size once again. If you don't remember, and we only went over it briefly, if I have sort of a parameter here that is not bound to anything, then I need to sort of bind it out here with this where statement. If I had more than one, why do I have two cursors? I might do something like u, v, or something for other parameters. But I don't have to here, I just have t. Oh, it is. Like this is in 1 sec. All right. Who wants to pick a function to make it into this matrix? Just needs to be a function that takes 2 values. Anyone? No. All right, I'll just do sine plus cosine. So f of xy equals sine of x plus cos of y. Index matrix I2 equals matrix 1 f. All right, and there's our matrix. I want to see a few things though, because I cut a few corners there, and I want to see if Julia is smart enough to have figured out what to do. This is something that will come as a surprise sometimes if you're a longtime Julia user. It used to be very often that you would have to do certain things in order to keep type stability, where your types didn't change randomly at output, where you had to keep performance, you had to do extra flags for bounds checking or inbounds. And then sometimes just randomly on a Tuesday, they'll release the next version of Julia, and that's completely unnecessary anymore. In the case of at inbounds, which was this macro that was like, I swear to you, I'm in bounds. You don't have to do the bounds checking. That actually became harmful. It used to be sort of like if you were a high performance computing person, you'd put at inbounds everywhere because you knew better, right? It turns out that this can be harmful to Julia because for two reasons. The first is that this is a sort of viral thing to say. If you say, I know that I'm in bounds and you don't have to worry about it, Julia has to propagate that upwards because it can't trust you, really. And so it has to compile two versions of every function that has this at inbounds thing. The second reason is that sometimes the bounds information can give the Julia compiler a lot of information, enough to compile away parts of your code or make it even faster. It's a little bit counterintuitive, but it is actually true. So let's see here. I'm going to do at code. Remember, we looked at some of the code at one of the at code macros earlier. You can see all of them right here. At code lowered is the first one. That's where we get rid of all the sugar, like the getindex notation, and we turn it into a function. The next one is at code typed or at code warn type. That's where we do type inference. And that's where we can see if, for some reason, your function isn't really amenable to optimization because Julia can't tell what the types are. And then the next one is at code LLVM. Julia uses the LLVM compiler internally, one of the best compilers in the world. And then finally, at code native, which is the machine code for whatever machine you're running. It'll be different for, probably 3 different models of architecture here in this room. So I'm going to do at code warn type. Let's see, do I need to put this in a function? Probably. Test func. That might be wrong, but so can anybody tell me why I'm putting this in a little function here? Talked about this a couple times about when Julia compiles things. It only compiles things when you invoke a function. So if I just do benchmarking or I do code analysis and I'm at the top level, right? I'm just in the REPL. I'm not actually giving Julia a chance to do any of the compilation that makes it fast. So it's generally good practice to put your benchmarks in a function. I'm probably being overly aggressive here. It's probably not totally necessary. But if you have a for loop, for instance, don't benchmark the for loop at the REPL. That'll be very, very slow. And I'm not even benchmarking here, but it's the same effect. I'm doing at code warn type, test func. Let's hope it actually runs the first time. Aha. Let's see, what is I2? Okay, I2 is correct. No, it's because I2 was a global. Silly me. There we go. That's the other thing that I just ran into, of course. Globals are quite bad. If you have a global, sorry, let me fix that again. If you have a global in Julia, you'll notice I know what I2 is, right? Julia should know what I2, but it has no way of verifying that this thing will remain the same throughout its runtime, right? Because we can rebind variables and all that sort of stuff and change things. Julia works really well because of this really arcane thing called world ages. I won't talk too much about it, but essentially when you enter a function, Julia is allowed to say, I'm done. You can't do anything else. You can't change anything else until I'm done with this function. Of course, if you then run the code again, add new code, it keeps the old world ages around so long as it knows that it doesn't need to update that function because you've added new code. So that's what allows Julia to be really fast and to not have to recompile every single time you change something. But global constants really defeat that. So I'm going to do this. And it looks like everything is all hunky-dory. The reason I was worried about this being type unstable is in this definition. Does anybody see the problem with this definition? each function has its own type. Remember. So function is an abstract type here. We are essentially allowed to put any function in there. And Julia can't typically tell what is in that slot. The other thing, though, is that Julia is very, very good at const prop and trying to figure its way around bad developers such as myself. What you might want to do instead, if you were to write this correctly, and it could fail in more advanced scenarios or more heavy code, is you would probably want to do something like this, where you parameterize on the function as well. That will potentially gain you a lot of performance back that you might have otherwise lost. All right, I think that's been about an hour. We talked a little bit about the AbstractArray interface and a little bit more on type stability. At code warn type is great. I'm gonna just briefly run through the rest of them. At code typed is good if you're eagle-eyed. It doesn't quite bold the problems like at code warn type does in bright red. At code LLVM is not for mere mortals to read. Certainly not me. And then at code native is honestly, I think, sometimes a little bit more legible than the LLVM is. It's pretty rare that you'll ever need to look at these, but sometimes it can be useful if something is really stumping you. All right. Oh, all right. My package. Let's go ahead and create a package together. So there's a couple ways to do this. Yeah.
Is there any way to increase the brightness or maybe like turn off the front end? I can't see any of the purple letters or.
I also can't see purple.
Yeah.
We will be back in Julia here.
No.
I thought I turned on high contrast. Let me try to find another.
You can make it white.
Yeah, the purple is.
I would rather not see the letter. Just gotta do it.
Is that what anybody wants?
You can't read it.
Maybe the light's turning off would be. Be like,
Maybe
What about
the only one.
tango light? What is tango light? Tango light.
These are all bad, but whatever. Update both modes. Okay. Wow. I don't know if I can code like this.
Hey, but I think is there white things that?
Huh?
There?
Where?
Like for this. Like, is that just space?
What? Yeah, that's
That's
just
odd.
let's just LS. There's nothing in this one, but like, yeah, it's just the spaces between the things. Oh my god, my eyeballs! It's like 3 screens of light.
To be fair, though, I
Like
also
in
use
portrait.
because I think it's easier.
So there's 3 ways to do this. There is the manual way, which I have not done in quite some time. And then there are 2 package templates packages. If you want me to do the manual way, I will slog through it. But I think I will show how to use one of the package templates just because it's probably best practice.
Can I just have to create my package one more time?
What? This one?
Yeah, that one. Thanks.
Let's just.
Okay, I have it.
Maybe we could just make it on this. So make packages
See, this is the thing.
folder.
And I can't read that. Can you? No, nobody needs to, but oh, I guess you can read it up there. I can't read that at all.
If you just do make folder, it might be the same.
Yeah.
So wait for this to compile for a second.
Yeah, but you could just make it right like this.
You can also make it a negative.
You can make it on VS Code, right? You just check the folder.
Why do I have Kaimon installed? Nobody knows. All right, I'm going to do using package templates.
Is there a file inside the package? So right now I just have an empty folder.
Nope, empty folder. If you are on 1.12.6, try to press enter and see what happens.
So what do you do to download all these?
Nothing. Just ignore that. That's just my computer. Try doing using package templates and see what it tells you.
Okay.
So yeah, I would do.
Package templates not found.
Does it give you an option to do something?
Import as.
It asks you to add.
Yep, go ahead and do that. So press Y or whatever.
Is this still inside QNumerics, the GitHub?
It doesn't matter. I don't, you know, it can be if you want it to be, so you can delete the whole folder. It doesn't have to be though. You know. All right. Everybody to that point, approximately. Okay. I'm going to open the help REPL because it's been a couple weeks since I've done this. And it's going to nicely pull up the README. So if I type in the name of the package in the help REPL, it will bring up the README of whatever your package is that you're looking at. I believe there's an interactive. So I'm going to do this and create an interactive template. And I'm going to name it T. Sorry for the folks that can't see at the bottom there. This is what I'm about to press enter on. So I should already have package templates in my scope. And I'm going to go ahead and press this. It's going to bring up a nice little menu for us. So the first thing, it should have your username already. Hopefully, provided you have GitHub set up or Git set up. We're not publishing this right now, so most of these details don't really matter that much. That's the correct authors, you know. I'm going to go ahead and have it put it in your all's dev folder, just because a lot of this is the default for most people. Yeah.
Hey, sorry, I'm not at this point.
Okay.
Could you go back to what you?
What are you looking for? So you should do using package templates. Did you get to that point?
I did type that, but it says it can't be found in the current tab.
And then does it give you an option to do something?
Run import package.
Yep. So you should be able to press yes to import the package. Julia is very nice these days. It used to be so nice, but now it'll tell you it's missing and it'll try to find it for you.
So it's give us a template keywords to customize. How should I customize it?
Did you do the interactive mode here?
I think you're making.
So then you should have this little menu that we're in right now.
So the names and the yes, you have the username and authors. Should I also add my username as myself?
If
you're planning to publish this package, it doesn't really matter though.
How should I edit that part? So I can use the up and down to format some part. I don't know how to add it.
Enter is to edit it, and then once you're all done, you press D. Right, so enter is a toggle. I'm showing you the, it'll show you, I'll show you how to sort of edit your own name. Yeah.
No method matching template.
What different does it
I
make?
got a method error. It says no method matching template.
I press, let's say open up to select the specific part, let's say for the user part. So I want to add my name. I will press the user button. I will
No, you select them all at once, then you press D for done.
different.
That's the issue that you're gonna
I'll get it. Oh, yeah.
They're done for the. Done for
Go to this one and I press let's see what I wrote down.
No, I mean, you didn't have your centuries.
Right.
Yeah, no, I didn't have my kids.
Okay, did you? Okay. Oh.
I was player.
And value for use.
You see Spider-Man?
Yeah. After we're done, I can try to solve it. but it's a little while. Yeah, thanks.
Value for.
Where GitHub username for the.
We're not publishing this, it doesn't matter. If you plan to publish it, you can change it. I'm gonna change the Julia base version. And then we can click also plugins. So I might want to change the plugins that I'm going to use here. You know what? I'll also edit this. So once I press D, I've selected everything with the enter, and I press D to say that I'm done with that part of the menu. And it'll ask you for a new user. So I'm not going to change that, but you can if you want to. If you have other authors, you can enter them at the next section if you chose to change that part.
So I just put a default
Yeah. So I probably had you prematurely make a folder. If you want to use that folder, you can type it right here. If not, this will show up in your dev folder, which is where a lot of people, if you type dev package in the package manager, that's where it'll send this package or that package. So might be a nice way for us to get familiar with the innards of .julia, the directory where Julia stores all of its sort of files. So I'm going to leave that there. Select minimum Julia version. I think I mentioned at the very beginning that 1.10 is the long-term support version. So a lot of people try to support 1.10. I don't care. I almost always just use the most recent version, unless it's a package that I really need to keep around. All right, so these are plugins that are available in package templates. A lot of these I wouldn't really bother too much with. One that you might want to use in the future would be Documenter. That's Julia's documentation system. We're not going to get far enough to interact with any of these really. But this is a great way to set these things up in CI in continuous integration so that you don't have to deal with them. It sets everything up pretty much automatically. You might have to twiddle with some of the files, but it's a whole lot better than searching around the internet trying to find what to type and where. If you want like a formatter, for instance, to run after every time you make a PR, formatter or runic are good options. If you don't have the Julia registration action, Julia registrator action already installed on your account, you can do that here. I don't anticipate any of you will be registering this particular package, so no need for that. So I'm done with this section. I know that you can't really see this very well now, so I'm going to move it up to the top here and try to do that. And so a lot of this, is just default stuff. If you want to change anything like the main branch to something else, if you use GPG, if you want to, so typically when we publish Julia packages, not typically, universally, how we've been saying like using about or using linear algebra. When we publish the package on GitHub or somewhere else, it's not just about, because that would be very nondescript. The way that we, the sort of URL that we use, or the name of the package, is about.jl. Every Julia package is sort of referred to by the outside world as package.jl, which is the sort of extension for Julia files. Makes it very easy to search for things. And so if you would like, in this thing here, you can turn it off. And so it will just publish your package as is. Maybe it's, my package is popular enough that you don't need the .jl anymore. We've seen a manifest several times today. If your package is about extreme reproducibility, for instance, then you might want to have the manifest in there. But most packages, right, are about reusability between people. It's only final code artifacts or projects that people keep on their local machines that need to be reproducible. Yeah, and the rest of these are pretty straightforward. License. Most people in the Julia world use the MIT license. It's what Julia was licensed under. Some people are moving more and more towards copyleft licenses, like GPL, for various reasons. But MIT is pretty much the default. I would say at least 90% of packages in the Julia world use the MIT license. You can customize the badges that you put on your README. You can customize the testing that's done. Aqua is Julia's sort of automatic code assurance, quality assurance package. Sort of does some tests on your code to be sure that it maintains a certain level of quality. Jet is down here. Shrinking my thing. My window here broke my radio buttons. Jet is a tool that will find type instability in your code, and it will error or produce sort of a failed test. So that way you don't accidentally commit or make a PR that dramatically changes your performance. I'm going to pretty much skip through all the rest of this stuff. Typically, people use GitHub Actions to deploy their documentation, and the rest of this is just pretty standard. And what did I get out? I got out this big template that I can save. I could serialize it somewhere. Where is it? There it is. It starts here. Or I could use it for multiple packages at a time. If I recall correctly, I put it as T, but just to be sure, I'll put it back there again. And then if we look at package templates one more time at the README, we can be sure that we're doing this right. So I don't put my package.jl because that would double the JL. So we're just going to do T of, put this back up, T of whatever you want to call it. Yeah, I'm going to call it my package, but I'm none the wiser if you call it I'm tired or I'm sleepy or I hate this. You can see it does a little bit of work for us up front, pre-compiling documenter, a few other things, downloading some of these things that are standard libraries like P7zip and OpenSSL. Wait, P7zip isn't, but and tests and TOML. All right, so I can go ahead and click this, and I might want to. Oh, I'm just going to open VS Code there, so I can see the code. .julia dev, and then my package. And now we're back in dark mode. But hopefully not so dark. Can everybody see that? I can change this to light mode, but all right.
Was that my package.jl supposed to be produced? Was that supposed to be produced automatically? My package.jl?
Yeah, all this entire thing that I just opened up was produced by the template. So every single thing right here was automatically produced. This part is automatically produced even if you just use Julia itself to generate the package. But things like the README and sort of run tests and the .github for the workflows here, this is all done by the package templates.
If it's not produced, I could just type my package.jl and follow from there.
Sure.
Okay.
So here's the thing, my package, the name of the outer folder doesn't really matter too much, but if you're going to publish a package, this module and the name of your package have to be the same.
Okay.
So my package is the name that you have to use from now on. You can obviously change the name to something else and try to get it re-registered, but yeah, in general, this module has the same name as your package, and that is final. All right. Excuse me. So you're welcome to continue from here and just write whatever you want. But I am going to do a bit of things that I believe you need to be logged in. Some of the rest of the quantum people might have something sort of similar on their plates. So the first thing I'm going to write is another little matrix multiplication. I'm not going to write a new array. I don't want to inflict that on you again, but I'm going to write a matrix multiplication on the field GF2. If you're familiar with that, it's just the Boolean field, right? And so with different, operators. So let's see. So I'm just going to close that here. I'm in my package. Typically speaking, what I would do is I'll create a new file here. This part, I'm just going to do GF2, like I said. So I'll make another little file here, and this will be the GF2 file. And in order to get it into my package, I will include that file. This is essentially a copy and paste. You should only include things once. And you should really only include things at the top level of your package. So your mypackage.jl probably won't have, if it's a big enough package, probably won't have much code in it. It will just be includes of other files, and it may be exports. So if you want users to be able to, if I create the function creatively named foo, where is the Zoom thing going? Oh, go away, please. I'm begging you. Thank you. Why can't I press enter? Thank you. And I want people to be able to use it just after they use my package. So if they say using my package in their REPL, the only symbols that they will have access to will be my package and the things that I export. So without the export, they will have to do mypackage.foo if they want to use foo. If I export it, it'll be available just in their REPL when they do using my package. So those are really the two things that you will see at the front of a package that is sufficiently large. You don't see much code, you don't see any computation. It's just include and export. All right. So the first thing I'm going to do is I'm going to do a little oracle so I can check to be sure that I am doing this right. Abstract bool, abstract matrix of a Boolean and B of a Boolean. And this is largely modular arithmetic for GF2. So we can do something like this. All right, that's just for checking. We probably don't even need that, but let's see. So we're going to do what we call a triply nested matrix multiplication here. It's the basic straightforward matrix multiplication. We're not going to do any tiling. We're not going to do any fancy transforms on the loop ordering. We're just going to do, I actually don't even really care about the GF2 oracle. Wait, I wanted to go back. Okay, I don't understand it anymore. All right. The first thing we have to do when we're going to multiply two matrices, we got to know how big they are. So N and K are the size of A, and K2 and M are the size of B. Sometimes, Julia, the current LSP, language server protocol server guy, will sometimes give you some spurious little warnings here. Possible method call error is the real culprit. If you see this on something that's plainly, obviously correct, just ignore it. We're really hoping to have a new language server up and going in the next year or two. I think I mentioned before that it's currently being stalled by this garbage collection of compilation problem. But this is one of the problems that we deal with in VS Code using Julia, is this sort of spurious method call errors. We might want to assert that these inner dimensions match. So what does this mean? An assert just says, if this is not true, I'm going to print this message and error out. It's largely similar to every other error, but you would typically see it somewhere like here, where we need to be sure that something which isn't reflected in the type system is some invariant is followed. All right. Next, we're going to allocate our output. We got pulses, and we're going to do N and M. So that's our output. One way to make this faster would be to make this into a mutating matmul where we pre-allocate the output. And that's faster for a number of reasons. First of all, because there's no allocations happening in this function, it's happening elsewhere. And you can sometimes like amortize those, right? If you're writing into the same function multiple times. All right. For J in 1 to M. You might also do, I think it's axes. Let's see, we won't bother with that. There are some better ways to do this than 1 to M, but sometimes it will complain about that and ask you to change what you're doing because it's easy to mistype. All right. And then what do we need from here? We need an accumulator. So we're just going to have false. This is not a threaded thing. I don't think we really had time to go over threads. This is a pretty complicated topic, but I'm happy to talk about it during the rest of the week. We need one more iterator. You'll notice that this is a double for loop here. So you're welcome to do that if you need to. It's JI. And then for L in 1 to K.
I mean, I did this. Would you go?
ACC. We can do another little updating function here. We don't have to write it all the way out. The XOR or XOR, I don't know, has a nice updating form. And we're going to do A, I, L, and bitwise and B, L, J. After the inner for loop, we'll collect our little accumulator and we will put it into our value here. And finally, we will return C. So This is essentially how you write any matrix multiplication in Julia with a triply nested for loop. Right. We happen to be doing this weird Boolean algebra, but if you replace this with a plus equals and you replace this with a times, this is exactly the same as any other semi-ring, right? If you wanted to be tropical, you could make it the max plus semi-ring. But any semi-ring in here will work, and you can even abstract over it. So one extension you might make to this is get rid of the GF2, and you might say that I'm going to take the semi-ring as my first argument, right? Because those are two functions, and we can pass those in, and they'll be specialized over, and we'll get a nice fast semi-ring matrix multiplication.
Right, what's with the XOR thing you were saying? Where you said ACC, you said you sent an XOR and made that symbol somehow?
Yeah, so I just like all the other latex symbols, I do backslash. I think that's backslash. And then I typed XOR. The Julia VS Code thing is pretty nice about sort of telling you what's available, auto-completing here. And so I can just click tab, and then I have the XOR. And there's an updating form of this where sort of I do right here, this would be ACC equals ACC XOR
It's me.
the rest of the right-hand side.
Okay, this.
All right. This is pretty straightforward.
Yes.
So I am going to open my REPL, and this is so big I can barely tell what's going on. REPL is now at the bottom of the screen. All right. So I'm going to do using my package. I should already be in this environment, right? If you remember, you look at the bottom, it should say Julia N is my package. If it doesn't say that, you're in trouble. So I'm going to do using my package, precompiled, very tiny little function so far. And what do I have access to, right? Currently, nothing else has been added to my environment, but I can do my package and see what is available. The first and the last thing, I'm going to ask you to mostly ignore, but the last one you've already seen before, right? That's the include function for my module. Each module gets its own sort of include function. Each module also gets its own eval function. I simply would ask you not to use eval as much as you can. Last year, we had 3 or 4 students who were very keen on using eval. This is the dynamic evaluation function. You can pass it any string of Julia code, and it will run that Julia code. The problem with eval is that you can use it anywhere. You can use it to delete methods, for instance, while you're deep inside the program, right? And so eval is essentially the biggest and the baddest of the compiler defeaters. You essentially can't use the compiler correctly if you are using eval within your code. So try not to do that. If you code in Julia for longer than I have, eventually you may find a worthwhile use for it. There are certain things that you can do. For instance, revise, that thing earlier where we were able to sort of press Shift Enter and stuff like that. That's based on eval, right? So there are good reasons to use it, but not typically much in the computational world. All right, so we can take a look. I don't really have a great way to move this up except to do, oh, wait. Okay, sure. I guess that works. I can close that.
Yeah.
All right. I'm going to do a little GF2 matmul. I'm going to do rand. You remember I can do rand over any domain. So I'm just going to do bool, and I'm going to do 100 by 100, and then rand bool 100 by 100. And I should get something like that. We can check to see if the Oracle did actually anything. I think the Oracle might be wrong, but let's see.
so.
Oh, 2. Did anybody catch that? I didn't have to press Control Enter or Shift Enter. I didn't have to do anything. I just had to click Save. When you are in a project, when you're in a package, revise is working at its maximum effect. So if you make a change, it's available in your REPL immediately. The only thing you can't do, and you'll have to restart your Julia session, is make changes to structs. So you can't really revise those still. If you're trying to do a kind of interactive exploration, just make a new struct with a new name. And if you're really trying to be super expert at it, you could say sort of like my struct equals struct temporary struct, and then change my struct every time that you add a new one. But you can't remove structs. You can't change them once they've been revised. That might change in like the 1.14 era. There's been active work on it, but it's very heavy on the compiler, right? It has to pretty much look back at everything and say, oh, I have to redo all of this code. Did I get that right? No, that's different. All right. Oops. I think I'm missing a constant somewhere in there. All righty. So I am going to, while we're working on this, we might add something like BenchmarkTools. You shouldn't publish a package that depends on BenchmarkTools because it's for benchmarking, right? And if somebody wants to use their package, they don't want this random package that isn't necessary in there. But if you're just working on the package early on, there's no problem with adding it to the product.toml and using it from there. Benchmark.tools is different than @time. So that's the other way you might benchmark something, is just using the @time macro. And the reason for that is that BenchmarkTools works very hard to measure the time that it takes your program to run accurately. If there's high variance, if it's a very small value, for instance, if your program is running on the order of nanoseconds, then you can't really trust a single run. Sometimes it can take 100, 1,000, and BenchmarkTools will try to balance those things and find the point at which it is statistically sure that it has a reasonable measurement for the runtime of your program. All right, so I'm using BenchmarkTools, and I'm going to time our first little matrix multiplication algorithm here. A equals rand bool 1,000 E rand bool. All right. So the first thing I'm going to do is just benchmark it, and that's using the @btime macro, and I'm going to do GF2 matmul A and B. Oh, I forgot my prefix because I haven't exported this yet. This is my package, right? And this will take just a minute. All right. We see it took about 540 milliseconds. If I want something more complete than just the B time, I can also do @benchmark. This is a super valuable tool for when you're trying to figure out if you've improved an algorithm or made it worse. And so this will run for a little while longer. And in the meantime, so this is what you get. I'm going to try to zoom out a little bit here so we can just see a little bit better. You get a nice little histogram. Most of them look better than this one. This one's just clustered very nicely, so there's no reason to do a ton more measurements. You can see the range of runtimes. You might think you want to take the average, but it's oftentimes perfectly reasonable to take the minimum. That's the true sort of speed of your computer, right? It's not going faster than the speed of light or something. It just means that that was the least noisy time that they ran the benchmark. You also get things like GC time. So if we were running garbage collection during our algorithm, this would be quite bad. Garbage collection pauses all of your computation to do mark and sweep, to remove things that are no longer useful in your program. Minimizing allocations is therefore one of the best things you can do to optimize your programs, and that therefore minimizes garbage collection time. And you can see we took 10 samples because this is a fairly heavyweight program. I'm just going to copy the next algorithm. It is an experiment to see if we can make things worse. This happens more than you would like to think. It's quite easy to damage an algorithm while you're trying to optimize it. So let's try the same little benchmark on this so-called dynamic version. And let's see if it takes any longer. It might not. Like I said, Julia is quite good at working around us humans. But I anticipate that this one will be quite a bit slower. And hopefully people can see why. I don't know how easy it is to read. So we've got some any's in here. I'm kind of forcing the issue, trying to make this worse. This is doubly bad because it's an any vector of any vectors. So lots of pointers, lots of allocations, and lots of inability to predict the results. So it looks like we are quite a bit slower because it's taking some time.
Wherever there is package, my package not there, not good.
I mean, you're not using device.
Maybe package template not there. I think okay, then I didn't get any of that. Okay, maybe ask for that.
If you're in a package using revise in the VS Code REPL, you typically don't need to press Shift Enter. No, you just need to save. No, while you're just using a package. So I haven't defined, you have to, when you create a package, you define what pre-compilation is, right? So you decide, hey, I know my users are going to use, the plotting function for the scatter graph quite a lot, right? Because that's a pretty common one. And so you would add that to your precompile workload because you don't want your users waiting every time for it to precompile. But Julia doesn't precompile on its own. That's entirely chosen by the package authors. Does anybody see the whopping difference we've got here? We are 60 times slower just because these two vectors right here were vectors of any. You might be fooled into thinking sometimes that this is not due to dynamic dispatch or something like that. Because at code born type so I see a lot of any's in here, but at the bottom I see I got a bit matrix in return. And so I managed to, because I just used C equals falses, I managed to recover the output type just fine. So you might ask, what's the problem? The problem is that whenever Julia encounters something within your function that it doesn't know the type of, it can't compile that call, it can't inline it, it has to do dynamic dispatch. So I'm going to pull up something down at the bottom here. So this is, for I think a few of you were interested in, this is the pipeline for how Julia gets compiled. So I have this function f of x. It calls the function g of x and h of x sort of dereferenced. This dereferencing is essentially if you have a vector with one value or a reference, you don't need to put one because it's just the one value in there. G of x has one method. And in this case, it's, a method for float 64, and we know that it's got concrete arguments, and so it's static. This X right here is a reference to any, and that becomes a dynamic call. So the first thing that happens is we try to compile F. We parse it, we do macro expansion, which is where we turn macros back into normal code, and we dispatch on F of 2.0. If we have a cache miss, that is, we haven't compiled this before, the first thing we're going to do is type inference. And type inference is what gives us this nice, I don't know what you call it, code here with all the pretty colors. Things that are correctly sort of inferred are typically colored in blue, but you can see there's some things that are inferred that still have any, like this here. The reason why this doesn't matter is because this is the constant any. So Julia is pretty good at just highlighting the things that you actually care about being potentially type unstable. The next thing that happens after type inference is optimization. So we knew that G was type stable. We knew it had concrete type, so it's inlined. We just put it directly inside of F. We know what it is, and it becomes nice and fast. H is kept as a dynamic call. I think one of our @code low-words earlier showed some dynamic calls, and that can sometimes be a sign of some sickness. After that, we do code gen, so we send everything to LLVM. LLVM creates native code, and we call F. The X squared, like I said, is inline from G, and then we hit H, and that's a dynamic dispatch, and we start all over. So this starts the compilation again, and this is why the dynamic one was so slow. It's not just that we need to maintain type stability on output, but also within the body of your function. It's super important. You can have some type instability within reason, but any's like this are quite bad. We are going to give this next little function a try. This is something that I've implemented before for GraphBLAS, this sparse linear algebra program. But when you're doing a lot of computation on these Booleans, I think I mentioned earlier, or we talked about it, or maybe it showed up in the abouts that we were looking at, that we store Booleans as 8-bit values, so a full byte, right? Even though we only need a bit. And if you're doing a lot of really big matrix multiplications, that can hurt your performance. So you can let's see if this works. Hopefully it improves. Like I said, sometimes you do a little bit of over optimization and end up on the other side of the cliff. And if you remember, I think we were in the around 546 milliseconds, that area. And by packing things, by sort of turning these bytes into bits so that we have sort of 8 bits in a byte, 8 of these Booleans we pack into one, we have gotten, 10 times faster, 50 times faster, something like that. Yeah, 50 times faster. So when you're doing a lot of things, in quantum numerics, in computational science, a lot of times before you go looking too hard for things like SIMD, if you're familiar with that, before you go looking for, grabbing a GPU, oftentimes you can get a lot of algorithmic performance gains by sort of examining your code pretty closely. This is obviously a little bit of a stretch for sort of most optimizations, right? You're not going to drive up to your laptop one day, sit down, and get a 50x performance boost on the problem you've been working on for months. But it is super important that you pay attention to the actual structure of your data. If you're able to fit more into the bits that are available to you, you can get a lot faster. All right. So I was told by somebody that GF2 is pretty common in quantum. I don't know. Y'all are the quantum people, not me. The next problem that I've been told is not uncommon is sort of a hot loop where you have to apply a lot of different operations that may have different types or may do different things. So we're going to go back to my package. We're going to create a new file here. Hot loop. And we're going to include our file so that it is available to revise and we can interactively develop with it. All right, so my understanding of this little operation is that we have a state vector and we have a bunch of in-place operations that we may apply in sort of an arbitrary order. And we may have to apply a lot of them. 12 different operations is something you could potentially unroll, right? You could just have a function that does these 12, but if the order or the number of these operations is an input to your function, it's a runtime value and you can't necessarily optimize over it. So the question is, how can we deal with this efficiently? So let's say that these are our little structs that represent our different operations here. We're using the semicolon as a new line. So the first one, we can scale something, we can shift the state vector, we can conjugate it, we can flip it, negate it, all these different operations, and they all have a different type. This is a little bit, what's the word I'm looking for? Extreme of a case, is my understanding. But it is very common that you will have these hot loops where you want to do something that is slightly dynamic, right? You may have hot loops that run over a union, a vector that contains a union, and it has maybe 10 different types in that union. And it's not always clear what the best way to represent that is. One of the ways that is pretty common, especially in the video game world, is to do what we call the structive arrays or array of struct conversions. So a struct of arrays essentially takes an array. If we have an array of many different types, we might turn that into a single struct that contains a lot of arrays. And those arrays are all homogeneous. And that allows the compiler and your computer to run over those arrays continuously and not lose performance sort of dealing with dynamically shaped data. But maybe that's not available, right? That can sometimes imply reordering. And it's a fairly difficult transform to do. You kind of have to change your entire code base. So I am going to just do a bit of bookkeeping here. So let's see. These are the functions I want. And I will post these if you want to examine them a bit more closely. And probably find correctness bugs. So we are dealing with this issue right here, and that is this union. You'll recall I told you that unions are pretty scary, but sometimes you have to deal with them. So our op union here is the scale op, the shift op, the same set of operations, all of a different type. And there's no easy way to represent this without these different types. If you did, one of the ways that you might do it is an algebraic data type. Julia doesn't provide those natively, but we can look at a package that does that. And for a long time, people used those packages extensively. So let's see. That is for the union or the ADT. And I'm just going to use this opportunity to show a little bit of benchmarking, because I told you earlier that you should avoid these loops as much as you can. And a loop. All right. So this uses the add the elapsed function or macro. The problem is I only have this over in my REPL. I haven't yet used it in the package. So I'm going to add BenchmarkTools here. I'm going to do using BenchmarkTools. It's important that we maintain access to our dependencies. And I think maybe printf too, using printf. Printf is a standard library, but it may not be available within the package without being used. Uh-huh. So if I have an error in revise, it'll turn yellow. And I have to do revise.retry. And it turns everything nice and green again. All ops. I'm missing some sort of constant. Oh, there we go. Oh. I don't really want to do the mochi. Yeah. I'm going to show you, so algebraic data types is this way to, for instance, sum types, is this way to sort of put a bunch of types together with a tag. And that tag will tell you what it is. It's an awful lot like a union. But algebraic data types hail from the functional programming world. And they're a very precise and oftentimes performant way to represent data that takes a lot of different shapes dynamically. And that tag is how you determine, you pattern match based off that tag. So I am just going to add mochi here. I think that's how you spell it. Yep, already have it. Oh, and then we have to go up here using mochi. That data not defined. Did not mochi. Oh. So here's something. We have this module, something that we haven't seen so far. We have this module, my package. If I were to put another module within my package called my module 2 or something like that, everything within this module would not be natively available to my package. Just like when we were talking about exporting foo, right? If it's not exported from foo, you have to use the dot syntax to get access to it. So Mochi puts a lot of its functions sort of deeper into these nested submodules for various reasons, to keep things clean, among other things. So I'm going to do, instead of using Mochi, I'm going to do .data, and then I'm going to grab the data macro. So that brings that into scope. I'm going to do the same thing for Mochi dot match, which is that pattern matching I mentioned. If you're interested in ADTs, we can talk about that more offline. But hopefully what I'm about to show you is that recent improvements in Julia's dynamic dispatch algorithm and its handling of unions makes most of these packages, which used to claim 10x, 100x speedup, mostly obsolete. It worked previously like that the past couple of days, but we'll see if it does again. Wait, do I need this? No, I do not. Okay. All right, so this little function will run. And while that's running, it will tell us sort of whether we want to be using a vector of any, a vector of type union, or this ADT. and we want smaller the better. And I believe what we're going to see, like I said, didn't used to happen this way. Unions used to be really, really bad for performance, and they still can be. But it seems like they're not so bad within hot loops anymore. The bigger problem is just they poison inference sometimes, right? If the output of a function is this big union, it's hard to optimize the next function, right? But it seems like at least when you're just iterating over some functions and they don't actually change the result type of the data, that these unions are dispatched very efficiently. So while that's running, does anybody have anything they're aware of that they want to explore a little bit more? We can look at some more tools for finding type instability. I would say we could look at sort of Julia's task runtime, but sort of parallelize things. But I'm not sure how helpful that's really going to be in the next hour and a half. Yep.
I lost in the middle part. So is it possible to share this terminal? I can try to see if I can catch.
Yeah, so I will share this package. I swept over a lot of things, right? My point here was to sort of show that I was talking about unions earlier on today and how they can be quite bad for performance. But one of the things that the Julia developers are very good at is taking something that is usually pretty bad and making it not so bad anymore. The code is a little bit complicated, but I'll comment it fully and put it on the same website maybe tomorrow. All right. So we can see this union here. The ADT, like I said, Moshi, used to, its big claim to fame was that it was much faster than using big unions. And of course, any we know is pretty bad, right? Any means anything could happen. And you can see as we get K, here's the number of elements in this vector of any vector of union or vector of ADT. And we can see that the union is really fast. It's faster than the ADT. It's faster than the any. What this means for when you're developing is that you don't necessarily need to fear unions of values in your vectors. You don't need to fear unions of values in sort of the things you apply to vectors, which Stefan told me was something that's pretty common. You apply a lot of small operations that are differently typed in a hot loop. And ordinarily, you might look for a way to avoid doing that. But in current year, in 2026, it's not so much of an issue anymore. So that's a big bonus. All right. I can keep going, sort of implementing random math things in this package. We can split up and sort of talk about any questions you have individually. It's up to you all. Next thing that I would do is sort of implement the complex number manually. So, you know, complex parameterized over type T. After that, I have run out of content pretty much, unless you want me to start sort of looking at GPU programming or tasking or stuff like that. But that's a lot to leap into without the full 3 to 6 hours that I would normally spend on that. Any takers on anything? Yeah.
Could you do like a brief overview of the GPU stuff?
Yeah.
Maybe wait for the actual class on that on Wednesday?
Sorry.
Sure.
Sorry, like.
Yeah, I was just gonna do K since I thought you weren't doing running on their computers. But that's fine. Yeah, there is a full class on that on Wednesday. I believe mostly focused on CUDA. Let me think. We can look at one of the parallelism notebooks.
Are there types specifically for sparse matrix?
Yeah, there are lots of them, actually. So let's see here. Wow, my eyeballs.
That's how we come.
All right. So Julia has a built-in sparse array standard library. I am one of the maintainers of it. It is honestly quite old. It's something that we largely wish we could sort of get rid of, but we're stuck with it in the Julia 1.x series because we need to maintain backwards compatibility. But it's hard to make changes to, and we don't really want to make upgrades to it because for one big reason, because we can't add parallelism to it. So, if you do A times B with dense matrices in Julia, if they're a sufficiently large size, Julia will use OpenBLAS or Bliss or Apple Accelerate, these really fast threaded BLAS runtimes. Unfortunately, we don't have access to that in sparse arrays because we originally wrote it in single threaded mode, and you can't sort of add threading without breaking potential other users. But it's still a reasonably performant implementation of the CSC matrix structure. So S equals sprand, 64. So sprand is sparse random. It takes the element type first, it takes the size next, and takes 0.05. Which is the density of the matrix. If I made it too much more dense than this, where's the bottom of my, I don't understand. What? Oh, I'm zoomed in or something. Weird. If I made it too much denser than this, right, it would effectively look like a dense matrix. I guess this one is a bit too small, but 0.5. As you get bigger and bigger in terms of density, you end up losing all of the performance benefits of sparse arrays. But I can do all the same things that I can do with dense arrays with sparse arrays in Julia. I can do linear solves. So are those not the same number of columns? What? Oh, wait. Wrong backslash. Sorry. S backslash. This is the second time I've done the wrong backslash today. So you can do linear solves. You can do S times rand of 100. And you typically get pretty good performance. You can do S times the full dense matrix, and you get the dense matrix. This is unlike the result of this is I believe occasionally. Oh, it is now always matrix. I'm not sure that it was always like that. So this is not something that we typically want, right? If I multiply S, a sparse matrix, by a full dense matrix, you would not expect to get a full dense matrix out. Actually, what is? Oh, I think this is just still too dense. Yeah, there we go. You would not expect to get a full dense matrix out. This is one of the other problems with the standard library, is that it's not very good at choosing the right data structure, right? This is clearly a sparse matrix within reason. And so we would probably want to store this in CSC or CSR, compressed sparse column or compressed sparse rows. If you're looking for other types of sparse matrices, there are other ones available. Oops. So we have COO and CSR. We have dictionary-based encodings. And then we also have block. There are block sparse matrices. And I believe a lot of the tensor libraries that the rest of the crew is going to be talking to you about use some degree of sparsity, although I think many times it's structural sparsity, not unstructured sparsity. I'm not sure if you were asking about structured or unstructured sparsity. I deal with mostly unstructured sparsity. Julia built into it does have quite a few structured matrices. So if I take the diagonal of a rand, whoa, wait, what?
Using linear algebra.
Well, I just don't know where my window went. Like, legitimately. What? It's not that one. What's this it? I think it disappeared. It's not on this one over here. It's not over here. Fascinating. Okay. Yeah, for real. I think it's actually when I turned on light mode that these things started to happen. So using linear algebra. So diag, I think. No, diagonal. Oops, I didn't do the question mark. So I can form a diagonal matrix from a random vector. This is too big to show on the screen nicely, so maybe 10. So here's a diagonal matrix. This is one example of a structured sparse matrix. Structured sparse matrices in Julia are a lot better at propagating their format correctly than the unstructured sparse matrices. So I have other formats as well. I can do tri-diagonal. Rand 9, rand 10, rand 9. So there's a tri-diagonal matrix. I also have other matrices which are not quite sparse, but they not quite structured sparsity, but they kind of imitate it. So this symmetric matrix here is not what you might find in like a packed symmetric matrix where you only store one half, like the upper triangle or lower triangle. In this case, it's just a kind of a mask or what we call in Julia a wrapper type that says, I'm going to choose one side or the other, and when you index into it, it'll just index into the other side of the matrix. But there's no extra storage space saved for this particular one. It's the same kind of type as when we looked earlier at the adjoint matrix, right? This is a wrapper. If I look at the dump of that, let me move this back up here. You can see that the adjoint matrix is just this type adjoint. It has the type float64, and it contains a matrix of type float64. And otherwise, it's just a wrapper, and you can unwrap it. For instance, I could do A equals that, and then parent of A gives us back the original matrix. It's the same with the symmetric matrix, which is one of the structured sparsity matrices. Let's see, are there other ones? We can sort of look subtypes of abstract matrix. And so these are all the sort of structured sparsity matrices that are available in Julia natively. Bidiagonal, Hermitian doesn't really count as structured sparsity. Sim tridiagonal, symmetric, and tridiagonal.
Then you have to remove this.
If you just and speed up.
All right. Does anybody else have any other interesting questions? Yeah.
I have a follow-up question on that.
Mhm.
So you said that the symmetric matrix is just a wrapper. It's not actually saving any space over storing the full matrix.
Mhm.
I guess why
Why not?
I believe the savings are often pretty limited and the computational cost can be somewhat high with symmetric packed matrices. There are libraries that do it, but Julia's base linear algebra does not. You don't actually gain like the like sort of half sparsity that you gain from it isn't really all that notable in the grand scheme of things, compared to for unstructured sparsity, you have to get down into the 0.01 density range for it to be even valuable, right? So you can imagine for symmetry that the space savings aren't always that crazy.
So I assume it's a similar thing with permission.
You do gain with computational savings, right? They exist for a computational reason, not for a memory savings reason.
Gotcha.
And largely speaking, both of those, Hermitian, adjoint, transpose, and symmetric, exist to dispatch to the BLAS, like the classic linear algebra programming libraries. And they do that quite efficiently. In many ways, Julia's linear algebra library and the early versions of Julia were what happened if you made open BLAS or the BLAS interface into a nice language on top of it. All right. Any other questions? I don't have any more for anybody. This is, I believe we get off at 10, so we're not that far off. Let me double check that. We're on QNumerics.
Super sir, I mean the main diagonal and
10:30. So we're about an hour early. Better than last year. Yeah. If anybody has any personal questions that they would like to ask about their own personal code, you're welcome to bring it to me. I'll be here for another hour. But I don't have any strong reason to keep you here. So you're welcome to skedaddle unless Stefan or somebody else does otherwise. Yeah.